A very good morning to Dr. Norazana. We are from group number 6. Today we are going to present our lab report on experiment 7, which is the TORRICELli theorem. To kickstart, I will present the abstract. In this experiment, we verified the TORRICELli theorem using a cylindrical tank with holes. TORRICELli law is a theorem that relates the exit velocity of a fluid from a hole of container. The exit velocity of a fluid depends on the height from flow to orifice. As the water level rises, water passage decreases, and thus the water speed also decreases. Next is the objective. Our first objective is to verify Torricelli relationship by comparing measured and theoretical value of velocity. Next is to find the relationship between the Bernoulli equation and Torricelli law. Next will be the introduction. Torricelli theorem or Torricelli law is a theorem in fluid dynamics that relates the velocity of non-viscous fluid flowing under the force of gravity. This law illustrates the significant relationship between fluid exit velocity and height of the fluid in the container. The speed of fluid flowing under the force of gravity out of an orifice is proportional to the square root of the vertical distance. The relationship between Torricelli theorem and Bernoulli equation results from the exchange of potential energy at the top of the container to the kinetic energy at the orifice. For theory and methodology will be presented by Dana.
Hi guys, now I will explain the theory and methodology of this experiment. So first we should take a look at this figure 1 first. So as you can see, the capital H here represents the height of the surface of fluid from the ground, and then the smaller h represents the depth of the hole from the surface of uh, fluid, and then v represents the velocity of the stream flowing out, and then the dx is the maximum distance covered by the stream of water. All right. First, if you have a fluid stands at the depth of h in an open tank whose side walls are vertical, so basically when we have a tank with the side walls which are vertical and then the height is h and with an open tank, uh, and then there's a hole in the sides of the wall, the velocity of a non-viscous fluid flowing from a cylindrical tank can be represented by the Torricelli theorem. So basically they're saying when you have a such tank with a hole with the vertical walls and the hole in the side walls, and the fluid inside it is non-viscous, which means it's not so thick. It can flow quite fast. The velocity of the non-viscous fluid when it's flowing out from the cylindrical tank can be represented by this Torricelli's theorem, which states the velocity of the fluid flowing out equals to square root 2 gh, and then h is the, as I said earlier, the depth of the hole from the surface of liquid. G is the gravitational acceleration, and then velocity of v is the velocity of fluid flowing from the cylindrical tank, right? The velocity of the fluid coming out of the spout is the same as the velocity of a single droplet of fluid that falls from the height of the surface of the fluid in the container. So what they are saying is the velocity of the stream of fluid coming from the spout or the hole here is equivalent to a single droplet of fluid falling from the surface of the water or fluid, right? So it's almost same as a single droplet of this fluid falling from this level, from the surface level to the ground, and the velocity of both scenario is same, right? That is what here series theorem states. Now, water stream from the hole is horizontal direction, which can be represented by kinematic equation. For this case, the velocity v at any point I can be represented by the time taken t by the stream to cover horizontal distance from a water stream dx. Okay, so basically what they're saying is you can use the kinematic equation in this scenario. So let's assume x is the distance of the water stream, and then x equals to v1 vi times t, right? So dx is difference of the in the distance of water stream. So basically, um, x naught is when the time is 0, and xi is when the time is I. All right. So this is the beginning of the experiment. This is the end of the experiment. Let's say it like that. So here you can conclude that dx equals to vi delta t plus 102 a t square. Okay. So and a is always 9.8 meter per second square, and at the initial point of v equals to 0. So basically the vi is at the initial point. So when at initial point v equals to 0, so vit 0 multiplied by delta t will become 0. So we can ignore that and straight away write the equation like this: dx equals to 102 a delta t square. And then note that the volume v and flow rate q, we it's missing here, flow rate q of the cylinder can be calculated from the following equation. Okay, here. Okay, there's a mistake here as well, right? So the v is velocity and equals to a h c w. W is the width of the cylinder, h c is the height of the cylinder, a is the area of the cylinder, and then q is the flow rate, and the flow rate is equivalent to area of the cylinder multiplied by square root 2 g h and w. So now we will move on to the methodology of this experiment. So first, the apparatus is set up based on three different stages of height as shown in figure 3. So there's h1, h2 and h3. For each set of results, we use different stages of height. So let's say the first set of results, we use h equals h stage is h1, the smallest, and then we'll move it up. The stage will move it up, and then we'll get another set of results. So then the second one is the water is filled into the cylindrical tank. So we fill water into the tank. And then number 3, we should always cover the hole when filling in the water because we don't want the water to go out. And then we stop filling the water when the volume inside the cylindrical tank is our desired volume of water. And then we slowly remove our finger from the hole. And then we must record the maximum distance of the stream, and then we mark it first by using clay, and then we also record the time taken for the water to run out of the cylindrical tank to actually calculate the flow rate. We record the time to calculate the flow rate of the water or fluid through the hole. And we have the procedures repeated by using different volume of water and the different stages of height. So different volume of water is to make sure that the Q is not the same, and then different stages of height to add in another changeable variable into this in experiment. Last but not least, the results were recorded in 3 different tables, as I said earlier. And what the only change here, the only variable that is changed is the height, right? As you can see here, but it's quite small. But I think I can show you. You see this one is 36.65 centimeter, while this one is 76.15 centimeter. So the height changes. That's the only thing that changed. That's the changeable variable, changed variable in these 3 different experiments. Not 3 different experiments, 3 different sets of results. The changing variable is the height. All right. So that's all from me. Thank you.
Now I will present results and discussion. So this is the table 1, which show the results when the height from floor to origin phase is 36.65 cm. And next is the table 2, which show the results when the height from floor to orifice is 56.45 cm. And next will be the table 3, which show the results when the height from floor to orifice is 76.15 cm. Next is the discussion. The first discussion is to explain the selection on dependent, independent, and constant variable. First, the dependent variable. There are two, which are the maximum water trajectory distance and the time taken for water to drain out. And for the independent variable, there are also two. The first will be the initial water level, and second is the height from floor to orifice. While for the constant variable, there are only one, which is the density of water. The choices of these variables is to fulfill the objective, which is to verify Torricelli's relationship by comparing measured and theoretical value of velocity. This will be finally separated into two parts, which is the effect of initial water level on the water velocity, and the effect of height from floor to orifice on the speed of water. The reason for the dependent variable is to find the measured velocity. We need to know how the height of orifice from floor affect on the maximum water trajectory distance and time taken for water to drain out, and thus calculate the velocity of fluid. And while for the independent variable, to verify Torricelli's relationship, we need to observe on the speed of fluid flowing from an orifice to the height of water above the opening. And for the constant variable, the density of fluid is the constant variable to provide a constant gravitational force for both theoretical and experimental equations as below. The second discussion is to clarify on how we can relate the Bernoulli equation with Torricelli law for the case. So show all the derivation and explain each step. The Torricelli law may be derived from Bernoulli principle and relates the velocity of fluid leaving an orifice in a fluid filled container to the height of the fluid above the orifice. The Torricelli law is derived from Bernoulli equation by equating the potential energy in the static head of liquid to the kinetic energy of the water leaving through the orifice as follows, which is P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus 2. The P1 and P2 is zero since it is in atmospheric pressure, and the velocity at point 1 is also considered zero since the movement of fluid is so small and almost to zero. Z2 is zero because we take that point as the datum. So the Bernoulli equation will become Z1 equal to V2 squared over 2g. And by rearranging for velocity, we will get the Torricelli law, which is V2 equal to square root 2g Z1. The third discussion is the percentage of relative error for the theoretical and measured values. The percentage error between the theoretical values and the experimental value of the velocity of fluid is calculated by the equations as below. So we got the percentage errors, which is VTH minus VMEA over VTH times 100%. And the average percentage error is equal to the sum of the percentage error over 5. So before we calculate the percentage error, we need to find the theoretical and measured velocity. So the theoretical velocity can be found by using the formula VTH equal to square root 2GH. And the measured velocity is VMEA equal to x times square root g over 2y, where the g is the 9.81 meter per second square. So the results are tabulated. So when the height from floor to orifice is 36.65 cm, the percentage error is 146.53%, and therefore the average percentage error is 29.31%. And next is the percentage errors for the height from floor to orifice at 56.45 centimeter. The average percentage errors for this case is 26.62, since the total percentage errors is 133.09%. And next will be the percentage errors for the head flown float or phase at 76.15 centimeter. The total percentage error for this case is 228.79%, and average percentage error is 45.76%. And the last discussion is the source of error and method to minimize the error. There are few sources that causes the error. First, leakage occurs at the cylinder around the orifice, and this will affect the velocity of water. And next is the orifice may not point to the correct direction, which is in front. And this situation will cause water to flow in wrong direction. Third, the hole may not fully covered by the finger before the experiment starts and causes some water flows around the hole. This will affect the initial water level and also the velocity of water. Next is the parallel error caused by the eye level which is not directly perpendicular to the scale reading when taking the readings. And this error will affect the accuracy of the data obtained. And last is the human reaction time towards the visual. The stopwatch may have been stopped too soon or too late, and either way will affect the readings. So in order to minimize the error, we need to take some few precaution steps. First, repeat the experiments few times to get more than one measurement for each reading and then find the average. Next, make sure all the leakage are covered before the experiment starts. And third, in order to minimize the parallel error, we need to make sure that the eye level is perpendicular to the scale that needs to be read when taking the readings. And last, place the tube at the end of the cliff so that we can get more accurate reading of distance.
Okay, now we continue into the conclusion and recommendation part. Okay, for the conclusion, we perform the experiment to confirm theoretically our relationship by comparing calculated velocity values and hypotheses. The water height is manipulated in the experiment. We determine the observed velocity and compare it with the theoretical value. We strive to calculate water velocity as the height of the water varies. We find that the water passage decreases as the water level rises, allowing the water speed to decrease. The percentage error that we obtained in the experiment was exceeded by 10%. We cannot prove it by 100% accurate in reading the pressure, but we still can minimize the inaccuracy of reading by repeating the experiment to get the average value. So this experiment involves some errors which affect the accuracy of the result. Therefore, we provided some recommendation are needed in order to get more accuracy during handling this experiment. There are several ways of refining the experiment and achieving the best outcome based on the experiment. Okay, first of all, we need to ensure that there are no leakage occurs at the cylinder around the orifice that can affect the velocity of the water. Before we go into the experiment, check thoroughly and make sure all the leakage are covered before the experiment starts. Next, we need to prevent parallax error. It should be taken at the eye level that is perpendicular to our eyes when we take the readings from the scale reading. To get the correct data and result, we need to avoid parallax error. In addition, the hole may not fully covered by a finger before this experiment starts and causes some water to flow around the hole. When the orifice does not point to the correct direction, which is in front, and this will cause water to flow in the wrong direction. For improved accuracy, we have to research the manual laboratory we have been provided before we run the experiment, so we can run the unit and procedure smoothly and completely understand them. Last but not least, in order to get average reading, the experiment should be repeated a few times to get better result. The variance from theoretical result would be minimized by this. Thank you.